Hi, I'm Bob Alsop with ShopSabre CNC. Around here they call me RouterBob. We're going to be doing some reverse engineering today on the IS408. You know, the key to making a good machine tool, it starts with the frame itself. And we build all these frames out of structural steel, the same thing they build bridges out of. They're all welded. And it's really neat. You look underneath and the welds that you typically don't see look as good as the ones on the outside. And that tells you the quality level of the company itself. Now, the other part to the frame then is the gantry. And these are tubular steel, once again, all welded. They're actually 1/2 inch thick walled. And we have tubular steel supports. So those are the 4 parts that make the frame of the CNC router. Now let's talk about what actually makes it move. Motion control actually has several parts to it. The first thing you have to define is the actual movement of the axis or the vector that it follows. Now here's how we accomplish that. First off, you see these precision ground contour guide rails. That's what things actually move on. And in our case, the spacing is determined by our engineering software. And of course, the gantry itself actually has milled surfaces so that we know that that line is perfectly straight. So that's where you start with accurate movement. And that's the case in all 3 axes. Now what actually causes the machine to move are the ball screws. We use precision ball screws in all 3 axes. In fact, the gantry has a precision ball screw on each end. And what makes those ball screws turn are Mitsubishi closed loop servo motors, and they actually have Mitsubishi glass encoders. And we use the most accurate glass encoders in the industry. Now let's go look at the last part of motion control, and that's the brain itself, the machine control. You know, we're really excited about the ShopSabre MMP machine controller that we developed. MMP stands for Mitsubishi Motion Platform. So we base the structure of the control itself on Mitsubishi technology, the same kind of components you might find on a $1 million metalworking mill. So that gave us a real structure that was dependable and very, very reliable. But there's another part of machine control that relates to the operator, and that is the operator interface. So what we tried to do was to make an interface that an average employee could be successful with. We were trying to stay away from having to require an engineering type person to run the machine control. In fact, Leonardo da Vinci is accredited with saying simplicity is the ultimate sophistication, and I think we've really achieved that with this interface. But there's another part to this also, and that has to do with how this machine relates to the outside. Since we're running that user interface in a Windows environment, that lets us also run our other software. So we may run cabinet software on the machine control, we may run other types of programming software. We can actually have network capability to the rest of the company. In fact, this machine can be remotely diagnosed because of all that. So that creates a really, really good control setup. But you know, there's one more part of machine control that has to do with accuracy, and let's talk about that. There's 2 actual methods that we use in machine tools to actually move things around. One is called rack and pinion, and one is called ball screw. And let's unpack those a little bit so you understand how each one works and why one is actually better than the other. And incidentally, at ShopSabre CNC, we have both. We use rack and pinions on our low-end machines because they're cheaper. But on our machine tool grade routers, we pretty much have to have ball screws. Well, let's break that down, okay? A rack and pinion basically has a rack that bolts to the side of the frame. That rack has teeth. And if it says helical teeth, that means they're curved a little bit. All right, now what meshes with that is a pinion. So it's a little gear that has teeth that match that, and when that pinion turns, the assembly moves. What causes that pinion to turn may be 1 or 2 different technologies. It could be direct drive, but typically it's going to be a belt drive system or a planetary drive system. That doesn't matter. If somebody tells you planetary drives take care of the backlash, that's not true. The backlash is determined because of the play that's required between the pinion and the rack, and that play is going to be 3 to 5 thousandths. If you don't have that much, the gantry binds, for instance, when you move it from front to back. All right, sometimes that doesn't matter. On cabinet parts, you may not be able to tell the difference, but when you get into real precision stuff, you'll be able to see it. For instance, if you look at MDF doors, which is probably one of the most difficult things we machine, or plastic or aluminum, somewhere on the table, you'll see that play. That play will show up, and you'll have somewhere on that table a defective part because that play shows up. Okay, on a ball screw system, you actually have ball nuts which have preloaded balls in there, and there's no play at all. They call that a preload system because there is no play. So that eliminates all the play that you get with rack and pinions. And that's why you see that technology on real precision machine tools in the metalworking industry. Well, we use that on all our axes here on these machines. It's funny, you know, the people who say rack and pinions are better sometimes because they don't really know any better. They don't understand the engineering. I'll use ball screws on their Z-axis. So you say, well, why don't you put rack and pinion on the Z-axis? Well, I hope that explains that. Now, let's look at the spindles. This machine has an automatic tool changer spindle. We offer those in a number of different horsepower ratings depending on what your machining needs are. It has an oscillating tangential knife. Tangential means that the knife actually turns as it follows geometry. And this is a 3D laser scanner. And this is going to be used for reverse engineering. So what we're actually going to do is scan a part and then actually produce it with this machine. We're able to do all that stuff because of a couple things. One is we use a balancing cylinder to actually compensate for the weight, and the byproduct of that is they machine really fast in 3D. And also because we use stiffeners, we get really, really good edge finishes. Now let's take a look at the table. This machine actually has a phenolic table, and it's a vacuum table. It also has some T-slots in it, and that tells me that the person that spec'd this machine wants to do a lot of different things with it. Typically, T-slots are used for fixturing so that you can clamp fixtures onto the table. Now, there's a concept of machine tools called work envelope. Let's talk about what that is. It actually is a 3D volume that the spindle can actually reach. So that's determined by the travel in X and Y and also in Z. Now, if we look at this table, the machine says it's a 4x8. Here's what that means. We've set this up with part locator pins to actually handle 4x8 sheets of material that you would typically use in panel processing. But there's actually more travel than that. If I measure the table, it's 67 inches. Well, this table was actually machined with that router spindle, so that means this cutter can reach that. So what that does is that gives me some travel that I can actually take advantage of in some special machining applications and special setups. So it's a really nice feature, and also it ensures that the table lines up with the spindle, and in most cases I really don't have to put gasket if I'm using a spool board, so it's a really nice feature. There's something else that I really like about how we design this, and that is the actual travel in Z is about 4 inches more than the clearance under the gantry. And the reason is that allows you to actually take advantage of that clearance. A lot of companies cut the machine short there, and you really can't machine what fits under the gantry. You have to subtract the tooling. We don't have that problem, so pretty much if it fits under that tool bracket, it works. So it makes a really, really nice system. Now, this is a vacuum table, and you'll notice on here, these are the vacuum ports, and one of the things that jumps out to me is how big they are. There's 8 of them, and those tie together to 4 valves. Now, actually, those valves are part of the vacuum system, and they actually fit into a frame member, and that becomes a plenum. So that becomes a large volume for vacuum, and that plenum is connected to the back of the machine with a 4-inch plastic tube, and that hooks to the F4 vacuum system or whichever vacuum pump you put on there. What that really does is it really gets a lot of vacuum to the part, and that's one of the reasons we don't have to have gasket, and the other reason is we really can hold small parts. So it's a really nice design, and it's very, very well engineered. Now, let's go into the office and let's look at the software and let's design our sign. I've been wanting to do a video on reverse engineering for a long time. Now, reverse engineering is basically part of 3D modeling, so let's talk about that a little bit. When you cut a 3D surface, you're typically using a ball tool, and you're moving up and down and back and forth with step overs, and when you cover the whole surface, you've machined it. All right, and the size of the ball is determined by how much detail there is in what you're trying to machine. Well, where does that surface come from? Well, it could be something you download. It could be clip art. That's a 3D surface typically. It could be something you downloaded from the internet, like a guitar body. It could be a solid model that you created in one of the modeling softwares. But what if that's not possible? What if it's too difficult to actually solid model? If I take this part, if I solid model it, when I get finished with it, it's going to be pretty mechanical and pretty symmetrical. This part came from a 100-year-old house, and we have to duplicate that. So, if you look at it, it's not perfect, and you see the tool marks from the craftsman. That's what I have to duplicate. So the way I did it is I actually set this on the machine table. All right, I used a laser scanner, and the machine basically went back and forth across there and created a 3D model of it. And then once I had that, then I was able to put tool paths. Now, let's take a look at what the model that actually came out of the 3D scanner. All right, this is the output from the scanning process, and if you look at it, you see our objects there. The rosette looks, I actually see the tool marks on there, so that the definition came out really good. Now I've got some extra geometry. You can tell on there that you've got a rectangle here. Well, that's basically where we defined the area that we wanted to scan on the table. So if you had a great big part, that would just be bigger. Now what we're going to do is we're going to take that 3D surface and we're going to actually bring it into VCARVE Pro and position it and toolpath it. So now let's go to VCARVE Pro and look at how we do that. Okay, I have VCARVE Pro open up. Let me go through each step on how you get from that scanned image to something that we can actually work with. Remember, in VCARVE, there's 3 steps. One is geometry, which we created with the scanning process, applying toolpaths, and the final thing is output and code. So let's bring that 3D surface in here. So we're going to create a file. The first thing I'm going to do is define the material size, and it's going to be 10 by 10, about 0.875 thick. Okay, we're going to touch off. We're actually going to tape this down to a spoil board, so we're going to actually touch our tools off to there. I'm going to make the origin the middle. The origin is going to be the center of the drawing, so when we put our boards on the table, then we actually line it up that way, and we'll hit OK. Okay, so now we've set the job up. Now we have to bring in that actual scan. So we come over here to the tab that says Modeling, and we select this icon right here that says Import a Component or 3D Model, and we'll find our model. We'll bring it in, and this screen comes up. And this one's a little complicated. You have to kind of figure it out. This determines where the model goes in space. Okay, well the first thing I want to do for sure is I want to center it. So I'm going to center the model. Okay. Now if we look at the edge here, you can kind of see where that is in space. The next thing I want to do is determine where the 0 plane is, which is the back of it, based on the image. So I happen to know that the finished part is actually about 3/4 thick, so I'm going to say 0.75. All right, everything looks good. Now here's something that's really, really critical. If you remember, when we looked at the image, we had a bunch of stuff we didn't need. We had that surface, we had some holes sticking out. We want to get rid of that. So we're going to click Discard Data Below Surface. And there we go. So now we have something to toolpath. If you look at it this way. Now I need to do one other thing. Once I do the 3D surface on this, I also want to cut it out. So I need a vector, a line to do that. So what I'm going to do is I'm going to select this right here. Whoops, let's select the component. I'm going to select this, and it will create that line. It actually created a line right there. I'm going to use that to define the final profile. So those are really the only things you have to do. And now what I'm ready to do is actually apply toolpath. So we've done the first part. We brought the geometry in. We've done the little operations we have to get rid of stuff we didn't need. Everything's positioned in the material. Now we're ready to talk about toolpaths. Okay, the first part of toolpathing is really determining where within the volume of material that the actual part's going to be. Now, remember when we brought the surface in, we basically knew what the thickness was of the final rosette. So we said, okay, well that's how thick we want this to be, and so that clipped off all that extraneous stuff we had at the bottom. But now we have to figure out where that fits in the material because the material's a little bit thicker. So we click this button right here, and if you notice this slide right here, basically moves that up and down. Good way to look at it is from the side over here. See where that's up in there? Well, think about, we really want it flat on the bottom, and we want to take off that extra material from the top. So let's set this gap below model at 0. All right, and we'll hit OK. Okay, so now we have that position. All right, now how are we going to cut this thing out? Well, what we'll do probably first is we're going to do a 3D toolpath. Let me show you the tool I'm going to use on that. This is actually a Vortex 2215, and it's an 1/8" ball nose at the tip. The shank is 1/4, and there's actually an 1.5" cutting edge. The reason this works so well is the conical shape is really stiff, so you can take really heavy cuts, and the tool doesn't break and it doesn't deflect. So now the 1/8" is pretty much determined by how much detail we have. They also make another tool similar to this called a 2205. Everything's the same except the tip's a 1/16. You know, it takes longer to machine, but once again, that's determined by how much detail your part has. And I think ours will be fine with the 1/8" one. Okay? What we're going to do now is we're going to do a finishing toolpath. So we'll click this icon. We're not really going to use a roughing pass. Now, I've got some choices in terms of of where I can actually tool path. I can just do the model boundary, I can do all the material. In our case, we just want to do the model. We've selected our tool. All right, now I've got a choice between raster and offset. Raster is a straight line, so I'm going to go back and forth to start with. That's a raster. And I'm going to call this finish 1. Okay, and we'll hit calculate, and you'll see the yellow bar at the bottom. You know something's going on when that thing's moving. Okay, there's our first tool path. Now let's take a look at it. So what's going to happen when we run that, there's our material, we'll slow it down. Simulation is your friend in VCARVE Pro. If it's right here, it's probably going to be right on the machine. If it's wrong here, it's probably going to be wrong on the machine. So we hit preview selected tool path, and you see it starts in. And since it almost starts in one spot, then that lets the bit actually cut its way in. So it works really well. And then from that point on, all I'm machining is the offset, or the step over. Okay, we'll speed this on up. And that would actually create that surface. But what I like to do when I'm using this is actually cut it from 2 different directions. I think you just get better detail. And to do that, it's not that hard. So what I'm going to do is I'm going to select that. I'm going to copy it. Okay, open it up. Everything stays the same except I'm going to change the angle. So instead of 0, I'm going to set it at 90. And I'm going to calculate it again. Everything stays the same. There's the yellow bar advancing. Okay, we'll reset our preview, and we'll just preview all tool paths, and there's what's going to happen. There's the first, now it goes the other direction. When you combine those two, you get really, really good resolution. Okay, we've got one more thing that we need to do. We need to cut out from the scrap, and we'll use the same tool. That's going to be a profile cut, so we'll select profile. We'll select our tool, the Vortex 2215. Now I'm actually going to make it deeper than the material thickness, because remember that the bit has a radius on it. I want to make sure we cover that. Okay, we'll let it do it in multiple passes. We're going to cut it outside the line. Now it's going to ask us for the vector to cut. And if you remember, when we brought this in, we basically had it give us that outline, and there it is. So we're going to cut that line out on the outside, and we'll hit calculate. This is normal. It's just telling me your depth of cut's thicker than the material. We hit OK, and we hit preview. Cuts through, a double click, and there's our part. Now we're going to actually hold this down with double stick tape, so I don't have to worry about tabbing or anything like that to hold the part. All right, so now we've created the tool pass. Now the next step is to actually output that for the machine control, and we'll do that next. Okay, we've created our tool pass, we verified them with simulation, everything looks right. Now it's time to actually create the output files to the machine. So what we're going to do is we're going to click on this icon. It brings this screen up. Right, now, output all visible. Visible means they're checked, so if we check them, we'll see them. And once again, all of this is done with one tool, so we don't really have to worry about tool changes. I select my post processor, and that basically formats a code correctly for the machine, and I hit Save Toolpath, and we're going to call it Rosette, and we're going to save it. All right, now we've created a toolpath for the machine. I'm going to send that toolpath by network out to the machine control. Let's go out there and let's make a Rosette. Well, we just finished the re-engineering project, and it's unbelievable. I can actually see the tool marks from the original 100-year-old part on our newly created part. That's absolute magic. If you have any questions, you can contact us at ShopSabre.com. Thank you for watching.